Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this section of the course, we are going to extend our understanding of temporal difference methods. In particular, you know that what we've covered so far is called TD0, and that there is a more general form called TD lambda. This section is all about how to extend TD0 so that we can get TD lambda. As you'll see, TD lambda gives you a trade-off between one-step learning methods, like TD0, and calculating the full return, like Monte Carlo. The first thing we need to learn about when discussing TD lambda is the n-step method, which is what this lecture is about. The n-step method works as follows. We know so far that the value function can be described recursively. We also know that we can estimate v by averaging the returns for many different episodes. And we also know from TD0 that we can estimate g itself by using our current estimate of v. It's worth asking, what is the most accurate thing in this estimate of g? Well, that would have to be the reward r, because it's an actual sample we got from our experiment. So it's plausible then that if we use more r's and less of v, that our estimate of g becomes more accurate. For example, instead of taking the first reward and then using v to estimate the rest, we can take the first reward and the reward after that, and then use the next v to estimate the rest. Remember that Monte Carlo is just the extreme of this, where we don't use v at all. Note that we can superscript g to tell us how many r's we're using. So you see how this gives us sort of a discrete transition from TD0 to Monte Carlo. Since Monte Carlo learning means that the agent can only be updated after the episode is over, and TD0 means that the agent can be updated after one step, then using n steps of the actual rewards means you'll have to wait n steps before your agent can be updated, so that you can form the target using the actual rewards you got. In general, if we want to use n steps of r, we would create the target as follows. For updating v, if we're doing the prediction problem, the update equation doesn't change. The only change is to g itself. The only thing you have to do is wait n steps before you can update v for the state you are in now. The same thing of course applies to both tabular methods and function approximation methods. This of course can be extended to the control problem as well, where we use q instead of v. If we're doing SARSA, the update will be in terms of the chosen action, and the chosen action will always be greedy or epsilon greedy with respect to q.